The average, or I would say the mass of this distribution, is more to the left here than this one. Here. It's a bit subtle, not so easy to see, but this is what we can see here. If we want to compare two distributions, in fact, there is another graphic which is very commonly used. It's not the histogram, which corresponds to a theoretical probability concept of the density of a random variable, the PDF, probability density function. Another concept associated with random variables is the CDF, the cumulative distribution function. We can do it also for data, and this is what I did here. So for a theoretical distribution, here is the CDF. It's for an argument x is the probability that the random thing is less than x. And for a data, well, you do it, except you interpret the probability as saying each of the data points you have has a probability mass of 1 over n, where I have n data points. So what you do, you compute this thing, which can also simply be done by sorting all the, so f of x is the number of points that are less than x, rescaled by the total number of points of in the sample you have, which can be done simply by sorting. If you look at all the values you have, you sort them from the smaller to the larger, and there is a step at each point where there is one. Here it's less illustrative. If you compare to that, we see clearly things like what is the variability, but here it's more useful for comparison. Right? We see very clearly here that one distribution dominates the other. Here dominates means smaller. So it's practically always in all of the distribution, it's on top, which means it's smaller, because the thing that is smaller here is the x-axis here. On this distribution, we read things like, if I put 0, 5 here, and I go to the x-axis, what do I obtain?
Median.
The median. It's the median of the distribution, the point that's in the middle. There are 50% point larger, 50% point smaller. Where do I read the mean of the distribution? Well, you don't answer because it's not possible, it's not easy. I mean, if you have a computer in the brain, you can, but otherwise, normally with our visual cortex, we're not able to compute a mean from that. To compute the mean, we need to be able to compute the integral of the derivative of this curve, so it's not something we see. But we see certainly the median and also the tail of the distribution. If we're interested in the very large values that are obtained with very small probability of being larger than that is given here. So we see that the tail of the red is also less than the tail of the blue. So we see everything in this curve. We know in probability that this function gives us all information about the distribution. So that's something very useful to remember. When we want to summarize a data set, here are the classically used things. The median, that we're saying, that's the point in the middle. If the number of points is odd, that's easy. If it's even, there are 2 points in the middle, so you need a trick to agree with which one, so you can take the average of the two or whatever else. Very often, we're also interested in the mean. That's the standard definition of the mean. There are other means, but the standard one is this one. 1 over the number of samples, the sum of the value of the sample. There is already a very large difference between the two. What difference do you see between the two?
The mean contains all points, that means it's taken down all the values, but median is less big than middle value.
The median is the middle value, whereas this one is not a value. It's true. It contains the sum of all. It's true, but we can say if you are the mean, that means it has to do with where the center of the distribution is, and the median also. So both mean and median are called centrality values. They give a first order information where are you in average. There are large differences between the two, and we will see that the two are not equivalent from many viewpoints. An obvious thing here is that the median is completely unchanged if I do a nonlinear monotonic change of coordinate, change of measurement system. If you measure a noise in decibel or in watt, you do a nonlinear monotonic transformation. Right? If you measure something or the square of something, you do a non-monotonic transformation. Sometimes it's not obvious which measurement system is optimal or is standard for a given thing. If I change in a monotonic way, but nonlinear, then I don't change. The median will be the change of the median. So if I have 1,000 noise samples, I measure them in decibel or in watt. The one in the middle will be always the same. Of course, the value in decibel and watt will be different, but the median will remain the median. If I do the average of decibels and watts, I'm not at all doing the same thing. Right? Especially the average will be very largely influenced by very large values. If you have a data sample where you have a few very large values, for example, it's not the case of this one, but imagine instead of this, you have one value that is 1 million and all the others are between 0 and 100. Then the single value of 1 million will inflate the mean, will make it enormous. So the mean, we say, is not robust. In contrast, if one value is changed, it becomes, instead of 100, becomes 1 million, it will perhaps not change the median. If it's a value that was already large, it won't change the median. Or in the worst case, it will change the rank of the median instead of the value that was before. It's one of the neighboring values. So the median is robust to outliers. The mean is not. So if you use the mean, make sure you don't have outliers. Otherwise, your values can be completely wrong. That's a theme that we will see is quite general. Nevertheless, the mean is much easier to compute because with a calculator you can compute it. Here you need to sort the entire data set. That means that whenever there's a new data point that comes, you have to resort everything. So computing the median incrementally is much more complex than computing the mean. So the mean also has its interest. To summarize the variability, we have seen that the second data set is less variable. We see it because the histogram is smaller. A standard measure is the standard deviation. The standard deviation is the average of the difference between the value and the mean. M is this M here, square. So if we square this, we obtain S squared. So the standard deviation is the square root of the average square deviation. Root means square. Now, for the average, you take 1 over n or 1 over n minus 1. We will see why the 2 exists. The default thing is to take 1 over n. There's no reason. But there are statistical reasons that in some cases explain why this could be a bit better. When the data sample is large, it doesn't make a huge difference anyhow. So most of the time we won't care. And something that's very interesting, because it's scale-free, is the standard deviation divided by the mean, at least for quantities that are positive. If a quantity can be negative or positive, this one is not very interesting. But if quantities are positive, for example, what is the power consumption of a device? You have some devices that consume a lot, some consume that less. And you can see what is the variability of your population in scale-free terms. Because if I measure x in some unit, m is in the same unit, s is also in the same unit, and this is called the coefficient of variation, is unitless. So it's a number that captures the variability of my distribution. If it is 0, what does it mean? It's constant, because if s is 0, that means the sum of those squares is 0. Each of the xi must be m, so 0 means it's the least variable thing. If it's 1, well, nothing special. 1 simply means the standard deviation is equal to the mean, which is already a large number for many practical cases. When we use median, there are similar things that can quantify the distribution. It is often called the quartiles, the 25% and 75% of the distribution. Where are they? That, in some sense, play a similar role to the standard deviation. This is more robust as well, a bit more complicated to obtain, and less compressed than this. So very often, we prefer mean and standard deviation because that captures very compactly all we want to know about the distribution. The mean gives where it stands, and the standard deviation, how variable it is. You probably have met the standard deviation, so what could we say about it in general? So the majority says none, which means something else, right? Which is not very committing, but is correct. It's true. It's very tempting to interpret in terms of distribution, and it's often true, but not always. What is often going together with the use of the standard deviation is the idea that the distribution is normal. Normal means Gaussian. For me, means the same. Right? So Gaussian distribution. For a Gaussian distribution, we look up the tables, and we have those magic numbers. Plus or minus 196 times the standard deviation gives you a coverage of 95%. And plus or minus 330 gives you a coverage of 3 nines. And if you do 6 sigma, you have how many? 6 nines. Or so the more sigma you give, the more nines you have here. But this is true if the data is normally distributed. Right? Now, are data sets normally distributed? That will be one of the themes. Very often, some statistical techniques work well if the data is normally distributed or close to it. If it's not, then things might be very different. Being normally distributed is not invariant with reparameterization of your problem. If you measure noise in decibel or in watt, if one is normally distributed, the other will not. If you measure the response time or the throughput, which are more or less 1 over each other, if x is normally distributed, 1 over x is not normally distributed. So you have those subtleties that sometimes may play a role. Very often we forget about them. We will discuss a bit when we can and when we should not forget about this. So right now, take-home message, an exact interpretation of the standard deviation is true with a normal distribution. If your thing is very different from normal distribution, and we'll see these are typically the heavy tail distribution. Heavy tail distribution is something where, for example, all the values are between 0 and 100, except once in a while there can be one that is 1 million. So you can have outliers that are part of the distribution. They are not measurement errors. Right? The level of the water on a river is typically something that does not have a Gaussian distribution. Right? Most of the time it's small. Once in a while it's huge, and when this happens it's called a flood, and it can be catastrophical, and that can be one every 300 years, and so those rare event things is what makes distribution not Gaussian. Right? If the engineers who computed the reliability values of Fukushima had not assumed everything were Gaussian, we would probably not have had the Fukushima accident, because they were assuming the height of the waves is based on Gaussian distribution based on what they've seen over the past 10 or 100 years, but it is not. The much larger values can happen once in a while. Concretely, tools for displaying this are called box plots. So those kind of things are called box plots. This is a summary of those two things using here. So a box plot puts a box with a little notch here for the median, and we'll come back with this. The width of the notch gives a confidence interval for the median, which I'll discuss in a second. And so box plots are typically based on the median and the quantiles. Whoops. So they give here, for example, the 75 and 25% percentile, and then extreme values are shown here. So that's another way, which is perhaps very compressed and is very often used as one of the most illustrative ways. You have two distributions. You see very clearly that in average, the new is better. It's also less dispersed. The box is smaller. And yeah, that's what you can see here. Here I'm showing different things which are called prediction interval and confidence interval, which I will explain in a second here. There are many other summarization that can be used, but we'll stay with what we have now. Depending on the domain, depending on the paper, depending on what you're analyzing, it may be that you're in a mini project that you're doing. In this specific field, people have used other summarizations, in which case you have to adopt what people will use. But with what we've seen, it's fairly sufficient. So now the real interesting stuff starts now. Confidence interval. That's a very important thing. It quantifies the uncertainty that we do about an estimation. For example, here, when I estimate the median of my distribution, I can just see it as a purely descriptive thing. Say, here are all the data points I've measured, and here is what I can say. It is that the median is this and the distribution is that. It's a bit an autistic approach. I say, this is what I have, I tell you what I see, and I tell you nothing else. In reality, we would like to go one step further and do some interpretation, inference. We want to infer things about the data. So what we would like to infer, for example, is A better than B? You want to sell to me a new software for your DBMS. Is it better than the old one? I want to infer that. So what I can infer is what is the average, what is the execution time gain that I will have by running the new versus the old. We can interpret that as the median or the mean, both exist, of the value here. This is the old, this is the new. We see the old is larger than the new, it's good. But then we could ask the question, since I have done an experiment that has only a finite number of results by nature, we are only on Earth and humans, we cannot know everything, we have only limited access to knowledge. There is some uncertainty about the result I've done. If I would do this experimentation with 100 trials or with 1 million trials, I would expect with 1 million I would have a better accuracy on the performance gain I have. The question is, can we quantify this gain in accuracy? How do I know how much more accuracy I have if I do 1 million versus 10? And where should I stop, incidentally, if we want to have some reasonably good confidence on the accuracy? So the first thing we will see is, how do we compute this accuracy? Here for the median is done here with the notches here. So those two notches indicate that with 95% probability, we believe that the true value of the median, which we estimate by the red bar here, but since it's only an estimate, we don't have the true value. The real value with 95% probability lies between those two bars. And the same here for this other one here. So of course that tells you a lot. If the red value is much less, but if the bars are huge, then you don't have a lot of confidence about the gain. You see it's better, but there's so much uncertainty that you're not certain. You can do this for the median. We will see with which formulas. You can do this also for the mean. Here is the mean in this other red bar, and the dotted lines are the confidence interval for the mean in the two cases here. So now the first technical thing is how do we compute this? So here I've done another thing, which is computing have done paired experiment instead of unpaired experiment. Unpaired experiment is when I run system A over 100 conditions, run system B over 100 other conditions. Very often that's all we can do. In particular, if you observe things in nature, you can't pair them. If you do a simulation, very often you can do better. You can do paired experiment where all your randomized nuisance factors are exactly the same in the two conditions, for example. If you can do that, then instead of comparing A versus B, you can directly look at things like what's the difference in performance. For each experiment, you did A and B for the same condition, so you can compare B minus A, for example. Here I did that, and I obtained the improvement. Here it's about another data set. So the improvement we see here is the histogram we obtain. Is there really improvement where there is no improvement if 0 is in the confidence interval, which here is almost the case, but is not. So we can say there is some improvement. Here, larger is better, because the mean reduction is this, 26.1, the value, plus or minus here, a confidence interval. So those are what confidence intervals are, but what are they really? First, and this is the important things to understand, when we do things that have concepts relative to probability in them, there is always a hidden assumption somewhere, right? Because probabilities don't exist in nature. If you remember your first probability course, depending on how it was taught, but there is always some number that you can assign to the occurrence of events, the probability distribution. This is a model. I mean, if I draw something from a box and I say the probability that I take this is 1 out of 10, for example, well, that's an assumption, which is probably true if I have a bag and I do things randomly. For other things, the assumption is a bit more difficult to see whether it's true or not. But probability is always based on a model. The simplest model is what are the numbers you assign to all the outcomes here. When we do a confidence interval, we start making assumptions about the things. What we will try to do is make as few assumptions as possible. You could do assumptions like all the things I've seen come from a normal distribution. That's a strong assumption. A less strong assumption is all the things I've seen come from the same distribution. That's what we can call stationarity. The different experiments I've done come from the same distribution. It has not changed over time. And they are independent. And this corresponds to independent, identically distributed here. Practically everything that is done in statistics assumes this, that the things you have seen are in fact the result of a simulator done by nature or by God or by the people who did your system. And the only thing you have access to is the result of output of this simulator. So this is how we can reason about things to do statistics here. For example, when I have looked at this data set here, I can assume there is a hidden distribution, which is what's the execution time. And what I've done is call 100 times a simulator that will return to me an output. Of course, that's not the reality. But when we do statistics, we assume things cannot be cannot be differentiated from this operation here. So we'll come back to this. The first thing we need is to be able to assume that the different things have been are IID, stationarity and independence, which is related to what we saw yesterday. If there is a strong correlation due to a nuisance factor that is the same in parts of the experiment and different in the other, then you break this assumption. If the first half of the experiments are all done at night and the second half all during the day, or the first half with mobiles that have a small socket buffer and the second one with mobiles that have a large socket buffer, then you violate this assumption. So one way to make it happen is, as we have seen, to randomize the hidden factors. We'll come back to that a bit later. There are ways to detect whether this is true or not. Assuming we have obtained that, here is what a confidence interval here. So as I said, we assume the data we have seen, x1, xn. To simplify, I'm assuming here this is just one number. x1 is one number, not a multidimensional metric. And I want to find a confidence interval for the median. So I can estimate the median by sorting the points, taking the point in the middle. And then I want to say, how much uncertain is this value? If I would redo the experiment a second time, so I would live in a parallel world, I would do it again. Because things are random, I would find a different value. How much different would it be? That's the question. A good estimation should have very small confidence interval. If the confidence interval is very large, probably estimation does not make sense, doesn't tell you any information. So how do we reason about it? We assume that the data we have obtained come from some distribution that is well defined, but you don't know it. There is a computer program, you cannot have access to the code or to anything that the computer is doing, only the output. This distribution has a true median. I call M05 here. So if I call capital F the CDF, the cumulative distribution function, it means this is the point that gives exactly 0.5 here. And we can interpret that when we compute the statistical median, in fact, what we're trying to do is what is the true median of this distribution. So this is what we will obtain when we talk of confidence interval. We will say the sample median that I have obtained, the median I've computed by sorting the numbers and taking the one in the middle, I want to see it as an estimate of the true median I would have if I would have access to the entire information. And we want to have some bound on the difference between this and the thing I have measured. So the thing I measured, I call it M hat. M hat depends on the data. Therefore, it's also random. Hopefully not too much, otherwise the whole purpose doesn't make sense here. But it is random. That's something that's often forgotten. When we compute a mean or a median, it is itself random. Again, hopefully not very much, but the whole point of the confidence interval is quantifying how much random it is. A confidence interval for the true median is something that I construct from the data. So I write it as a function u of the entire data set. U is the lower bound, v is the upper bound. So I give you the data, you number crunch them through some algorithm that returns u and v. You claim this is a confidence interval. Well, it is truly a confidence interval with some confidence level, for example, 95%, if it is true that whatever you do, the probability that the true value is in the interval is at least 95%. That is what is meant by a confidence interval. So the true value will be within the bounds with that probability. How can we do it? Well, we look into textbooks and we find formulas. Here is the formula for the median and other quantiles. I looked up many textbooks, and in fact, this formula is well hidden. There's only very advanced statistics books that have it, so I put it in the lecture notes here. Other confidence intervals are very, very well known, but this one is much less well known. Here is how you obtain it. So you order, so the data points I have are x1, xn. When I put the parentheses here, means I sort them from the smaller to the larger. So x parenthesis 1 is the smaller, and x parenthesis j is the jth one. Then to find a confidence interval for the median, what you need is to compute indices j and k and take the values that are covering this interval, xj, xk. For example, if n equals 10, if I have 10 values, I've done 10 times an experiment, I sort the 10 values, then the theorem here says the value of j and k are 2 and 9. So if I have 10 data points and I want to have a 95% confidence interval for the median, it's not very good. I remove the smaller, I remove the larger, and the interval I obtain is the only thing I can say about the confidence interval for the median. It's not very good because I have only 10 data points. Statistically, 10 is not large. If I have 32, then I take the 10th and the 22, which will get a bit better. And in general, if I have a large number, the theory says if it's larger than 71, you have this approximate value. Say you take the floor of n over 2 minus 0.9 square root of n. So it will move like square root of n. For example, for the data set we had here, the confidence interval for the median, we had 100 data points. So it says we take the 40th and the 61st here. That gives me a confidence interval at confidence level 95%. Now you could say, why 95%? And to be honest, we don't really know. Other than, if I want to be more sure, for example, 99%, then we can use the same result here. But of course, as we can expect, is the confidence interval will increase. If If I want to be very sure, probably I have to have a very large interval here. Where does this result come from? So this result, which is given here, is saying I look at two indices j and k that are related to this is the binomial distribution. They must satisfy this. The coverage of the binomial distribution between j and k, between j minus 1 and k minus 1, must be at least gamma. Gamma is, for example, 95%. 0.95 here. I will not, we will not do many proofs in this course, but here, just to give an idea that this is not black magic. For example, say n equal 10. I assume I have received 10 data points. I assume they come from some unknown distribution. And the theory says that with probability 95%, the median of this unknown distribution is between the second and the 9th point. This is what we need to verify if we want to verify the theorem for this specific case here. For this specific n and this specific coverage, 95%. So what we want to prove is that if I have this setting, this probability is true. So for that, I will consider an oracle who knows the true distribution. And for each data point, we'll declare a success if the data point is less than the median. Otherwise, we'll declare failure. Right? So we see that I call capital N the number of successes. So the number of data points that are less than the median. Now, what does it mean that out of n experiments, I have seen, out of all my experiments, I have seen exactly k successes. So it means that k values are less than the median. Right? Now, if I sort all the values, saying that k are less than something is saying that the kth one is less than something. And it's exactly k, so that means the following one must be larger. So this is what this event means here. Right? Now, what is the probability that n is equal to k? Well, what's the probability, for example, that x2 is less than m05? We see that if I ask the question, is the second value less than 0.5, that corresponds exactly to the case that n is larger than 2. So in general, we can relate the PDF of the random variable n to the thing that we're interested in, which is the thing that will give us the confidence interval. So the event, this is less than the median, is the same as this thing here. Now n is what? N is how many times you succeeded in a trial. It's like flipping a coin. It occurs, the oracle would say yes or no with probability 50%. So this has a binomial distribution. The distribution n is binomial here. So if we continue and look at the other thing we want a confidence interval that bounds in two things, we obtain this thing here. So if we put all of this together, we see that the event that we want to check what is this probability is the same as saying that here. Now, here, whether the thing is less than or strictly less than doesn't make a difference for a random variable that would have a continuous density. That has a density, a continuous random variable here. So if we ignore this subtle thing here, we see is this event true is the same as that. That is saying that the binomial random variable is between 2 and 8. So this is why we have the binomial distribution in computing the confidence interval. Okay, so this is perhaps not so important, but the take-home message is if you want to compute a confidence interval for the median, Or for other quantile, there are similar results that are given in the theorem for the 75% quantile, for example, or the 99.9% quantile. What do you need to do from your data? You need simply to sort all the data points, go to a table that is a statistical table that's independent of your data, depends only on the confidence level and the number of data sample that will give you what are the ranks that you need to care about. So that's the standard formula, standard method, which is not very often used, but is the best one if you can, because, as we have discussed, the median is a robust thing. Very often, what we do instead is confidence interval for the mean. Here, right? So here, it's, whoops. Okay, timing out. So for today, I think we will stay with that. We have plenty of time next week to continue the discussion about the confidence intervals. How do things continue? So you have plenty of things to do for this course. You have to go through the lecture notes, to do the exercises, the paper pencil exercises, which is a preparation for the tests. But also in parallel, do a programming assignment to exercise all of this. That will prepare you for the mini project as well. So the idea is that in the following 2 hours of today, this is the self-service hours where we are here to help you with any questions you can have, but you work at your own pace on the assignment, on the lab 1. There was the issue of whether the test should be on Wednesday, as I had planned in my big master plan, or whether we want to move it to Tuesday. I have not received any objection. I posted a message on Moodle. Did anybody see the message on Moodle? Yes, okay, so that works. On Moodle I said we wait until tonight, so there's still a chance for somebody who is sick or wants to do the course and cannot. So tomorrow we will do the change. There is still a side effect that the lab is to be returned on Tuesday so a lab nominally is for, what we call lab is the programming assignment. A lab is for 2 weeks, so lab 1 is meant to be done this week and next week, and returned Tuesday of the following week, which will also be the time there will be the test. So those things are unfortunately synchronized. If this is you're well-educated engineers, so you should be able to manage your time such that you can know when to do what. So I propose for the time being to leave it as it is and see for the next, at least for the first lab, because it was posted and explained. So what would be more reasonable is perhaps to anticipate a bit the deadline of the lab, to have it returned on Friday night, for example, instead of the following Tuesday. We'll discuss that for lab 2, perhaps. Okay, thank you very much.